On the first day of classes back in 2017, we had a partial eclipse. What's different about the April 8th, 2024 eclipse?
Well, it's great to be here. We're really excited for the eclipse. So the difference of the eclipse that's coming up on April 8th and the one that occurred in 2017 is that we're expecting a total eclipse on April 8th, and 2017 was partial, as viewed from Dallas. So first, an eclipse occurs when the moon passes between the Earth and the sun, and the moon casts a shadow on the surface of the Earth. Where you are on the Earth will determine how this looks from your viewing location. So a partial eclipse occurs when just part of the disk of the sun is blocked by the moon. A total eclipse occurs when the full disk of the sun is blocked by the moon, and we're fortunate enough here in Dallas to be expecting a total eclipse on April 8th. This will mean that the surrounding area will look as if it's completely cast in night. So it'll be a very spectacular event, and we'll have a great viewing location here in Dallas.
Professor Olness, why is Dallas such a great viewing spot?
Well, we're very fortunate that we're very close to the center of the path, or the center of the shadow, or the umbra, as it's called. And so we're actually going to have almost a full 4 minutes of total eclipse here. This is very close to the maximum. If you go a little bit south toward Ennis, you can get up to 4.5 minutes, but then you'll get to enjoy it with about 1 million of your close friends and neighbors because of the crowds. And you're only going to get an extra ½ minute. So we're close enough. We're going to get 4 minutes of total eclipse here, which is pretty spectacular. Given the anticipated crowds and traffic, you're better off staying here. If you want to head to Ennis, you probably might want to start driving now because they're anticipating a lot of people coming to Dallas. So the partial eclipse it'll be a total of just over 2 hours. But the part you don't want to miss, the total eclipse, will start in Dallas at about 1:40. And that's 4 minutes of a total blockage. And that's the part, prepare for it, be ready, and do not miss that. That's going to be exciting.
So I'm really interested in the phenomenology, and some of our audience members are as well. Is it the case, I mean, since the light is affected, do we see color differently, if we can see at all during a total eclipse?
Yeah, very good. So this is something called the Purkinje effect, that during the lead up to totality, the sky and the surrounding area will darken very rapidly, much more rapidly than we're used to when we're standing outside. And so colors will appear more muted in the lead up to the eclipse than in a typical day. This has to do not with the changes to the physical properties of the light, but rather with the way that our bodies interpret that light. In particular, as we shift toward darkness, our eyes shift toward using the sensors in our eyes that are more sensitive to light and darkness, as opposed to those that are more sensitive to different colors. And our brains then perceive the colors that we're more sensitive to persist longer into the darkness than those that are not. And as a practical matter, what this means is if during the solar eclipse, you're near something that's bright red, you will notice that it appears to darken faster than things that are green or blue. So if you want to experience this on eclipse day, wear a red t-shirt, and you'll notice that your shirt will appear to darken faster than the surrounding things, and that has to do with our perception of the light and not any physical changes to it.
And in fact, to be more specific, you should wear an SMU red t-shirt eclipse day.
Indeed, indeed.
Continue on the same line of phenomenology. How close do you have to be to the eclipse to be able to experience some of it? I mean, not everyone is lucky enough to be in Dallas, but how much of an eclipse, like what percentage roughly, do you have to have so you can have some effect and see something unusual?
So you can see the effects with the pinhole camera or with eclipse glasses, even down to 10% totality or something like that. And so almost all of the continental US will be able to experience some aspect of the eclipse. The change in the shadows, that is sharp versus fuzzy shadows, you'll start to be able to notice that around 50% totality or something. But crescent shadows, or the partial blockage of the sun's disk, you can see even at 10% totality. You can notice weather changes. You can notice a cooling of the air and changes to the wind. At about 30 to 50% totality, you'll start to notice that. It'll be very dramatic the closer you get to totality. Things will feel noticeably cooler in the lead up to the eclipse. Another thing to pay attention to, another thing that you don't require totality for, is to listen. Just listen to how wildlife responds in the lead up to the eclipse. Birds and insects and squirrels are much more sensitive to the changes in temperature and wind patterns, and they'll pick up on it much before we recognize those shifts. And so just listen to the activity of the insects and birds around, and you'll notice changes in the lead up to the eclipse.
I guess I never thought of the fact that an eclipse can affect the weather. Can you say a bit more about how dramatically, like, are we going to have a blizzard?
Nothing quite so dramatic. It will be noticeable. You don't have to pay too close of attention. You'll notice it gets significantly colder in the lead up to the eclipse. Wind patterns will change. Also, I should say there's a temperature gradient. So if you're very careful, you can notice that the ground will stay a bit warmer than up above the ground. So you can notice a noticeable temperature gradient. And this has to do with the fact that unlike the change from day to night, which is relatively gradual on a given day, this is a very rapid, effective change from day to night. And so all of the changes occur much more quickly and over a much shorter distance within space. And so you can see the transition region much more vividly during an eclipse because the transition takes place more quickly. Wind patterns will change also. And so one thing to note is if there's a little bit of cloud cover on eclipse day, don't get discouraged. If those clouds are wispy and relatively light, often those types of clouds will dissipate in the lead up to an eclipse due to the changes in pressure, wind pattern, and temperature. Now, if it's fully overcast, we're probably out of luck, unfortunately. And if you're free to do so, then you're better off driving north or south along the path of totality if you can avoid the traffic. But a little bit of cloud cover, don't get discouraged. That kind of thing can change in part due to the influence of the eclipse itself.
If it were a full cloud cover, will we still experience the darkness, right?
We would still experience the darkness. And yes, you would still notice that it gets significantly cooler. It would still look like night for about 4 minutes. We would not, however, unfortunately, be able to see the corona of the sun because that'd be until.
Yeah. If I can add, if you're in a coastal region, of course, basically for the eclipse, you have the sun, moon, and earth all lining up, and that affects the tides. So you get particularly large tides. So if you're in a coastal region, you'll notice that, particularly if you go to some place where they have characteristically large tides, like the Bay of Fundy or Mont Saint-Michel in France. They're going to have extra large tides. That means very fast tides coming in and out. So if you're in any sort of coastal region, you'll notice that independent of the darkness.
You mentioned the alignment, and I'm thinking back to when I was a kid, there was the song about the dawning of the age of Aquarius. When did astronomers first start to understand like alignments and things like that? I mean, I'm wondering how superstitious ways of understanding the eclipse turned into scientific ones. Do we know anything about that?
That transition took place with the ancient Babylonians and the Greeks. So once it became clear that we could start predicting these phenomena, it very quickly led to constructions of models of the solar system, or as they would have called it, the universe, that allowed for some mechanistic understanding, at least to make sense of when these things occur, why they occur with some regularity. And so that transition occurred roughly around the 6th century BC or so. And then it really started getting formalized in about the 3rd and 4th century BC, and has persisted ever since, at least in the cultures that had access to Greek records. And of course, that's only developed further, and the biggest change thereafter occurred in the scientific revolution, about the 16th century AD.
Interesting.
So if you go back to the old models, I mean, you had this celestial sphere, and the ancients viewed it as, there was a celestial sphere and the stars were painted onto it. And then what they couldn't figure out was the planets, because that didn't fit the model. And in fact, they were called the wanderers because they would wander among the stars. So, that is some of the older picture of the universe.
Can I ask you, for people who joined us late, to remind everybody of the safety concerns we should all be aware of?
Just briefly, do not look directly at the sun in any case. The best is to use a official ISO approved set of solar glasses. And if that's not available, then I recommend using a pinhole camera to see a remote image. But do not look at it. Do not look at it through a camera. Any other suggestions or?
Yeah, I'll just mention you can take off your glasses during totality. So when the disk of the sun is blocked, you can view the corona with your naked eye. Your camera can get distorted, especially if you have a telephoto lens. If the disk of the sun is not obscured, it will fry the sensor effectively because you're focusing the very intense rays of the sun down onto the sensitive CCD that is used to record the image. So roughly speaking, whenever you need to cover your own eyes with Eclipse glasses, you should be using a solar filter on your camera and vice versa. So the only time you can take off your glasses is during the 4 minutes of totality when the disk of the sun is totally blocked and you can view the planetary.